Ladies, our study today is in section 5.5 of your textbook, and we're discussing normal approximations to binomial distributions. So we're going to learn how these two can coexist and one can be used to help calculate the other. Before we move into our first goal, let's review binomial probabilities. Recall that a binomial probability has only two outcomes, either a success or a failure. The mean of a binomial probability is n, the number in the sample size, times the probability p, probability of success. The standard deviation, sigma, is equivalent to the square root of n, the number in the sample size, times the probability of a success, times the probability of a failure. So let's take a look at this example just to review. Consider a surgical procedure that has an 85% chance of success. When a doctor performs this surgery on 10 patients, find the probability of 9 or more successful surgeries. Let's begin by identifying our variables. N would represent the number in the sample size, and in this case, that's 10 patients. P is the probability of success, and in this case, that's 85% or a probability of 0.85. And Q would be the probability of a failure. So if we have an 85% probability of success, we would have a 15% probability of failure, or 0.15. And remember, you just subtract the probability of success from 1 in order to calculate the probability of failure. Okay, so this is asking us to find the probability of 9 or more successful surgeries. So the probability of 9 or more, greater than or equal to 9 successful surgeries. Recall that we would need to find the probability of 9 successful surgeries and then add to that the probability of 10 successful surgeries. We stop with 10 because that is our sample size. Now, how do we find the probability of 9 and the probability of 10? Well, because this is a binomial probability, we will use the binomial distribution table in the back of your textbook. So if you will turn to page A8, that is where that table begins. So in the table, we first know that our value for n is 9. So keep turning pages until you find n equivalent to 9. And then we go across the top until we find our corresponding p-value, our probability of success. So with n was equal to 10, so we would start here, and then we would go down until we find our, in my table it says R, in your textbook it has the letter X here. So we would go down vertically until we get to 9, and then we would follow 9 across until we are lined up with the probability of 0.85. And that would be right here. Okay. So your textbook, I believe, takes it out to 3 decimal places, just like this screen that I'm showing you. So 0.347 would be your probability of 9 successes, and 0.197 is the probability of 10 successes. So let's replace probability of 9 with 0.347 plus the probability of 10 with 0.197. And when we calculate that, then the probability of 10 or more successful surgeries is approximately 0.544. And we know this is not unusual because it's greater than 0.05. Okay, so that reviews how we use a binomial distribution. Let's look at the second bullet point. What if the doctor performs the surgery on 150 patients? Find the probability of fewer than 100 successful surgeries. So n changes to 150. The probability of success is still 0.85. The probability of failure is still 0.15. Because it's asking for the probability that fewer than 100 of the surgeries are successful, then we would add the probability of 0, the probability of 1, probability of 2, we would continue to add all the way up to the probability of 99 successful surgeries. Now, that would take a long time. We have 100 different values to look up and 100 different values to understand and to add together. So it's not practical in a case like this second example to use a binomial distribution. So when it's not practical, rather than using a binomial distribution, we'll use a normal distribution to approximate the binomial distribution. So the point of this lesson is to know that when it is not practical to use a binomial distribution, we can change what we're doing and use a normal distribution to approximate for us. So let's look at that in goal 1. What I'd like for you to do is to pause the screencast and turn in your textbook to section 5.5. And that starts on page 275. And so I would like you to read the first page on page 275 and then turn this back on. All right, hopefully you've read that first page. So our goal here, goal number 1, is to determine when the normal distribution can approximate the binomial distribution. And because it says when, we know that we cannot always use the normal distribution to approximate the binomial. So let's look at this. We're going to let n represent the number of independent trials. That's our sample size. P is the probability of success in a single trial, and Q is the probability of failure in a single trial. So that has not changed. So what did you learn as you read? In order to use a normal approximation to approximate a binomial distribution, we have to have two things that are true. N times P has to be greater than or equal to 5, and N times Q also has to be greater than or equal to 5. And notice that's an and. If these two products are greater than or equal to 5, then we can use a normal approximation to calculate a binomial distribution. All right, so why is a normal approximation valid? Because this information is true. And I want you to see that here in these examples, in these graphs. The first graph shows us that n is equal to 4. So we have 4 trials. Notice that n times p and n times q are both less than 5. Well, this graph is skewed right. It is not normal. Okay, as we've learned, when we increase the sample size, we become more normal. But if you look, n times p is still less than 5. N times q is greater than 5, but they are not both greater than 5. So while it is becoming more normal, we still do not have a normal distribution. Now take a look at what happens when we increase the sample size to 25 and 50. Both NP and NQ, their products are both greater than or equal to 5, and the same when N is equal to 50. And look at their graphs, how they are both getting closer and closer to normal. So, what can we say happens to the shape of the binomial distribution as n increases? You could say that the distribution becomes more normal. And remember, normal means bell-shaped. Well, what do you notice about the value of n times p and q times p as the histogram becomes approximately normal? Well, we could say that both of them are getting larger, and they should get larger because n is getting larger. And specifically, they're not only getting larger, but they are becoming greater than or equal to 5. So that's important to note. If we don't meet these two qualifications, then we cannot use a normal approximation to approximate a binomial distribution. Before we go through Goal 1 examples, I'd like you to stop what you're doing and read in your textbook page 276. Once you've read 276, Try Goal 1 examples. Then turn the screencast back on and check and see how you did. All right, so the instructions said decide whether you can use the normal distribution to approximate X, the number of people who reply yes. If you can, find the mean and the standard deviation. So 62% of adults said they have an HD TV in their homes, so 38% do not. You select 45 adults in the US and ask them if they have an HD TV in their home. Well, if we're trying to calculate the mean and standard deviation, we first need to see if we can use the normal distribution. I've already calculated the product of n times p and n times q, and both are greater than or equal to 5. So yes, we can use the normal distribution. So to find the mean, we multiply n times p, which we've already calculated, and the mean is 27.9. And then our standard deviation, we know, is the square root of n times p times q. So our standard deviation is approximately 3.26. So the mean number of people in the US that have an HD TV in their home is 27.9 with a standard deviation of 3.26. Let's take a look at number 2. 12% of adults in the U.S. who do not have an HD TV in their home are planning to purchase one in the next 2 years. You randomly select 3 adults in the U.S. who do not have an HD TV and ask them if they are planning to purchase one in the next 2 years. So if we find the product of n times p, we immediately see that 3.6 is less than 5. So we cannot use the normal distribution to calculate this mean and standard deviation. Because the product was less than 5. So we'd have to use other means to calculate the mean and standard deviation. All right, so a little more review of binomial distribution. Remember, the binomial distribution is discrete. Remember, those are numbers that you can count, and they can be represented by a probability histogram. To calculate exact binomial probabilities, the binomial formula is used for each value of x, and then the results are added together. And geometrically, this corresponds to adding the areas of the bars. So we can either find using the table, or if we know the area of the bars, we can use those. So I'm going to stop here for goal number 1, and I'd like you to read page 277 and then turn the screencast back on, and we'll move on from there. Or actually, I'm going to start a new video for goal 2.